Okay, this lecture we're going to finish up with our discussion of acid-base titrations, and then we'll introduce the concept of solubility. And last time we talked about when you had a titration with a strong base and a strong acid, and how that would look and how you'd calculate the pH at different points during that titration. Today what we're going to be going through is when you have a weak acid and a strong base, how that titration would look. And then the other options, of course, are if you have a weak base and a strong acid, that titration, or if you had a weak base and a weak acid. And the titration curves are, I think, summarized pretty well here on the title slide. Right? They have, if you just wanted an overview of how, the titration curves would look, this is a pretty decent overview. Could be a possible exam question, right? Give you a picture of a titration curve, and then you have to match what kind of a titration it is. So the material we're going to be covering is in chapter 19. The first two sections are dealing with acid-base stuff, so we're talking about the titration curves in section 2, and then we'll also be going on to section 3 with dealing with solubility. Let's look at the first condition where we have a weak acid and a strong base titration. Now, if you remember what the titration curve would look like for a strong acid, strong base titration, you'd have a kind of a flat region down here. The pH would be much lower to start. It'd be pretty flat, and then it would rise up very quickly and then flatten out again like it does up here. And the equivalence point, the pH would be at pH 7 when you had a strong base and a strong acid. Now when we're starting with a weak acid, the pH is much higher to start. Okay? And you'll notice that it's not, a flat region here. It sort of kind of curves up. It has its own sort of sigmoidal shape here. Right? And that's what we refer to as the buffering region. That's where you're adding your strong base, and the pH isn't really changing a whole lot. Okay. And this inflection point here, whatever pH that occurs at, is the pKa of your weak acid. And in this case, it's 4.89. You'll also notice that now our equivalence point, this inflection point, if you would take the first derivative of that and find the peak, where that would be is the pH at the equivalence point, and you'll notice that it's not 7 anymore, it's actually higher. And that kind of makes sense, right? Because we're using a weak acid and a strong base. So the strong base is going to overwhelm, and the pH will reflect that it's a strong base. So it'll be the equivalence point pH is going to be a higher pH value. The molecular scene shown here, what's happening? Well, where we start out, we only have our weak acid, okay? And then as we add NaOH, what happens is the OH group is going to pull a proton, and that's shown here by you're pulling a proton off one of your weak acids and making H2O. And of course, the other part of that NaOH was sodium. Okay. So you do that, right? And this would be the region where you have about half of that gone, half of your weak acid gone. So that's where that pKa value is going to be. Then at the equivalence point, you've added enough of your NaOH to fully react with that weak acid, so equal molar amounts. Okay, and you see there now you don't have any weak acid left. All you have is your conjugate base of that weak acid. Right, so when you add more OH, there's nothing to react with it, and you're in a sense you're adding that OH, and it's going to change the pH very quickly. So how do you calculate the pH during points during this type of a titration. Those are summarized here. I probably won't spend a lot of time going through this, but you'll have these for your notes. Okay, so the initial pH, hopefully we all remember how to calculate the initial pH. You use the Ka value of your acid. And from that you can solve for H3O plus, and we went through how to do that. Your pH then is just your negative log of your H3O plus concentration. Well, what happens if you've added some base, but it's not reached the equivalent point yet? Well, in that region, you're going to be in the buffered region. Okay, and so that makes calculating the pH sort of easy, because you can use the Henderson-Hasselbalch equation, right? If you're in the buffered region, you start out with just weak acid, but as soon as you add some of that strong base, what's going to happen is it's going to convert some of your weak acid into the conjugate base. So your system's going to have that weak acid and its conjugate base and be a buffer. So we can just use the Henderson-Hasselbalch equation for that. Right, pH equals pKa plus log of base over acid. All right, at the equivalence point, right, remember at a strong base and a strong acid, the equivalence point, the pH is just 7. But for a weak acid and a strong base, it's going to be different. It's going to depend on your Kb value of your conjugate base. So you can set up your equivalence reaction as such, right? Your conjugate base plus H2O is going to be your weak acid plus OH minus. You can find that OH minus concentration, right, using this equation. You've solved for your, you find the conjugate base concentration by using the moles of weak acid you started with. Okay? And at the equivalence point, all of those moles of weak acid will have been converted into your conjugate base. You divide by the volume of your weak acid you started with plus the volume of the base you've added. Okay, so that's how you would calculate that. Kb, if you're not given Kb, which most likely you won't be, you'll have to convert it and calculate it based on Kw divided by Ka. Right, and then your H3O plus concentration, then if you want to substitute this into here, this equation would be Kw divided by the square root of Kb times the concentration of A minus, or conjugate base. Right? And that's important because you need that to calculate a pH. Okay, so your pH at equivalence point, again, is going to depend on your Kb value. Beyond the equivalence point, you would need to calculate that OH minus concentration, and that's going to be equal to the amount of excess that you add divided by the total volume that you have, and then you convert it to an H3O plus, and then finally use that to get a pH. Okay, so let's try a practice problem using that concept. Okay, so here we have a titration, and we have to calculate the pH during this titration. We're starting with 40 milliliters of 0.1 molar propanoic acid, which is abbreviated as HPR, and it's a weak acid. Ka is given. Okay, and we have 4 different scenarios, right, to kind of correspond to the starting, before equivalence point, at equivalence point, and then beyond the equivalence point. Okay, so let's do the first situation. We have at the very beginning, what would our pH be? So again, we need to write down, helps to write down our reaction. Propanoic acid plus H2O goes to PR minus plus H3O plus. Right, so when we put that in solution, that's going to be the equilibrium we get. We're starting here, 0.1 molar. We don't have any of these at the start. So we're going to get a certain amount that dissociates. Again, this, we're just assuming that it's about what we started with, and these are X. Then our expression for Ka is there. That's going to look very familiar. X times X divided by your concentration, so it's just X squared divided by 0.1, and we know that equals 1.3 times 10 to the minus 5, because we're given that Ka value. All right, so we can solve for H3O plus. It's just going to be X in this equation. And it equals the square root of 1.3 times 10 to the minus 5 times the times the concentration of weak acid. So that's 1.1 times 10 to the minus 3. And our pH is just going to be the negative log of that value. Which is 2.96. Right, so it's a weak acid. We're starting with, in the titration, we haven't added any base yet. It's going to be an acidic pH because it's an acid, but it's fairly high. It's not like 0 or 1 that you would expect on a stronger acid. Okay, for the second part, we have the amount of base that's added. We're going to need to, because we've added, in this part, we've added 30 milliliters of 0.1 molar base. So that's a fair amount of volume, right? 30 milliliters, because we're starting with 40 milliliters of acid. So what makes these difficult is you have to calculate the number of moles you have starting of your acid and the number of moles of base you have that you've added. And then you have to calculate the concentration that would be based on the total volume you have at any particular point. So let's do the initial acid. So initially we had 40 milliliters, which is 0.04 liters, and the concentration was 0.1 moles per liter. So we're going to have 0.004 moles of acid to start, and base, our base added is 30 milliliters, 0.03 liters, times 0.1 moles per liter. So that equals 0.003 moles. Okay, so now we have the number of moles. If we divided, if you want to divide that to get a concentration, right, the total volume now is going to be 30 milliliters plus 40 milliliters, the volume of the base plus the volume of the acid. So 70 milliliters total. So you can calculate concentrations. So our concentrations here, I'll write those in blue. So for acid, the concentration would be 0.057. And for the base, that concentration is 0.0429. Okay. Actually, the acid would be 0.0571. Okay. So we'll keep track of those in blue. Okay, now we can write our reaction that's occurring. So when we add base to that solution of weak acid, right, we're adding OH minus, strong base, it's going to be reacting with some of that weak acid to convert it into its conjugate base. So that weak acid, in a sense, is going to eat up the base that's added and be converted to its conjugate base. So you can keep track of this in terms of either the moles, the number of moles, or you can do the concentration. So we'll do both. And you'll see that they're actually the same. So we started with 0.004 moles of acid. We're adding 0.003 moles of base. Don't have any conjugate base to start. Not concerned with water. Okay, so what happens? Well, you're going to react fully. The full amount of OH minus will be gone, so you're going to lose 0.003. And when you do that, you react with the same amount of your weak base. And you're going to produce that same number of moles of your conjugate base. Right, so then your new concentrations will be 0.001, 0, and 0.003. Right, we could do that with concentrations as well. So that's typically what we have been doing. So if we use the concentration here for your weak acid, that was 0.0571. This was 0.0429. And that was 0 to start. So you're going to lose, again, all of your base. Lose the same amount of your acid. And gain that amount of your conjugate base. It's something like that. Okay. So now we have the amount of weak acid left remaining after we've added the base, and we have the amount of our conjugate base that has formed. So we have weak acid and conjugate base. That's our buffer system, so we can use Henderson-Hasselbalch. So pH equals pKa plus log of base over acid. So our pKa, we weren't given it, we were given our Ka, but we can find a pKa just by taking the negative log of it. Right? You can remember that based on a pH is the negative log of your H plus concentration, right? You're taking a negative log of something, in that case an H, proton concentration, to get a pH. Well, the same thing applies to really anything. So a Ka value, a pKa value, you would take the negative log of Ka. And we add the log of base over acid. So if we wanted to do number of moles, that would be base would be 0.003, and acid would be at the end 0.001 after we've added that strong base. And when you do that, you should get a pH value of 5.37. And we can do that same thing with concentrations, right? If we plugged in the concentrations in that, it would still be the same Ka value, so negative log of 1.3 times 10 to the minus 5. But then we'd add log of our concentration of base, 0.0429, divided by concentration of acid, 0.01424. And that's going to equal, pH equals 5.37. Okay, equals the same. So you can do that extra step to calculate the concentrations for this, or you can just use the number of moles of each. It's kind of your choice, or depending on how you're given the units in the equation, in the problem. Okay, so for part C, we're at the equivalence point. So we're at the equivalence point. So the amount of base equals the amount of acid. So base would be 40 milliliters times 0.1 molar. So we'd get 0.004 moles of base added. So we can again look at that, what reaction's happening when the base is added, right? You're converting to your conjugate base. So if we started with 0.004, we add 0.004 of our base. We don't have any of this to start. What's going to happen? Well, all of this is going to react, right? It's reacting 1-to-1. They equal. So at the end, you're not going to have any acid left. You're going to have only your conjugate base. So this is a situation that looks a lot like when we've talked about adding a salt of a weak acid into solution, right? So if you had, like, instead of the acid form of it, you'd have the sodium salt version of your acid. So like acetic acid, you would add sodium acetate into solution, right? So you just have the conjugate base, and it's going to act like a base, right? So if we wanted that concentration of our conjugate base, right, it's just going to be the number of moles we have of it divided by the total volume, which in this case is 40 milliliters to start, and we've added 40 milliliters of our strong base, so 80 milliliters total. So our concentration now is 0.05 molar. Right, the other thing we need is a Kb value, because this is the conjugate base of the weak acid, right? And remember, conjugate, the Kb of a conjugate base is just Kw divided by Ka. Kw is 1 times 10 to the minus 14. Ka we were given as 1.3 times 10 to the minus 5. So this would be 7.7 times 10 to the minus 10. Right, so we have Kb, we have concentration of conjugate base. Now we can calculate our H3O plus concentration. Right, and the equation that we're given on the previous slides to do this was Kw divided by square root of Kb times concentration of conjugate base. Right, so you can use the equilibrium expressions to derive these, or you can kind of just remember them for these situations, whichever one you prefer. So now we can plug these values in. Kb is 7.7 times 10 to the minus 10, and our concentration was 0.05 molar. And when we do that, we get 1.6 times 10 to the minus 9 for H3O plus. Okay, and then again, pH is going to be the negative log of that. Which is 8.8. Okay, so the equivalence point now, right, we're adding a strong base to a weak acid, so the equivalence point should be basic, above pH 7. Okay, and then finally, the last situation we have is after the equivalence point, we've added an excess amount of our base. So we need to determine how much excess we have. So how much base did we add? We've added 50 milliliters, 0.05 liters of that same 0.1 molar solution, which is 0.005 moles. Right, so we can, you can probably do this in your head, but if we just do it the long way, focus on the reaction that's occurring, right? We're starting with 0.004 moles. We're adding 0.005 moles of base. None of that to start. So we're going to be losing all of our conjugate acid, producing that, weak acid, producing the conjugate base. So we'll have none of that left over. Now we have an excess of base, so even after that reaction, we have 0.001 moles of it. And we have 0.004 moles of our conjugate base. Right? So now to determine our pH here, we're going to be focusing on this remaining OH minus. Okay, that's going to we don't really need to consider the conjugate base anymore because these moles of the excess moles of OH minus are really what's going to be driving the pH. So we can calculate that concentration. So we have 0.001 moles divided by our total volume, which in this case we've started with 40 milliliters, 0.04 liters, and we've added 50 milliliters, 0.05 liters. So that equals 0.0111 repeating moles per liter. Okay, so that's OH concentration. What we really care about is H3O plus because that is what we use to calculate pH. And so remember the relationship with Kw, OH minus, OH minus times H3O plus has to equal Kw. So you can use this to solve. If you know one, you can solve for the other using that Kw expression. So this is something like 9 times 10 to the minus 13 molar. All right, and then pH is just going to be the negative log of that. Which will be 12.05. Okay. So that makes sense. It's going to be a pretty high pH because we've added enough base to remove all of our weak acid, and we have some excess. So the pH is going to be quite high. Okay, so that a good summary on how to solve a question like this at any point. So you could probably expect on an exam to have to solve, have a problem like this where you have to solve this a type of question, a weak acid titrated with a strong base at different points in the titration. You can have the opposite. You can start with a weak base and titrate in a strong acid. We don't really go through this specifically in the class, but if you were to do that, the titration curve would look like this, sort of backwards of the weak acid strong base titration, where you're going to be starting at a higher pH. You have a buffered region here, and then you're going down in pH because you're adding a strong acid. Okay, but the points are very similar. And how you would calculate pH at certain points in this titration would be somewhat similar as well. Okay. The last thing we'll talk about in this section is acid-base indicators. The acid-base indicators are usually weak organic acids. That color is going to be changing when it changes from the acid form to the basic form. The ratio of that difference between acid and base is governed by the pH, or the H3O plus concentration of the solution. And because of that, you can use these to monitor the pH of a solution. The color change in these is usually over a specific and very narrow pH range. So here's a chart of some of these indicators. I think the one that is most commonly used, at least in lab, is phenolphthalein, and it's kind of a pink color, and you'll see the pH range it has. All right, and typically when we're using this, we're doing a lot of times what you're doing, at least in like high school, I remember, is strong acid, strong base titrations. But you'll see that the pH here is 7. That's where the equivalence point would be in those situations. But this doesn't change until like pH 8 to 10. Okay, so you really, when you see the change in this, if you're doing a strong acid and strong base, you've really gone a little bit past that equivalence point. But it's a good estimation. For the purposes of doing a weak acid, strong base titration, remember in the propionic acid, the equivalence point was something like 8.8. Phenolphthalein would be a perfect choice for that. Right? You do not have to remember these or memorize them. Right? If you definitely be given these values in a problem if you needed them. If we just looked at this, it's probably easier to see if you take a solution of this, and this is bromothymol blue. If it's below pH 6, it's kind of a yellowish orange color. pH 6 to 7.6, that's where you're getting this change at. So it's a mixture of the two colors. And above pH 7.6, it's blue. Okay, so here you can use this indicator to tell you about like the pH range that you're in. You're either going to be below 6, 6 to 7.6, or above 7.6. And how that would look if you overlaid your titration curve on these, like for a strong acid, strong base, right? That equivalence point is going to be kind of between methyl red and phenolphthalein. So I guess you could actually have both of these in solution, and when you get to that point where it's, you've seen the transition from this one and you haven't yet seen this one, you're at equivalence, right? But neither of those would work perfectly with that. You could use phenolphthalein again for a weak acid, strong base titration, because that color change is going to be right in the equivalence point. And then for a weak base, strong acid titration, right, methyl red would work very well because that equivalence point is going to be in that color change region. Okay. And what we haven't talked about yet, but would be a little bit more complicated, is when you have a polyprotic acid. So you have something like H2SO3, it's a weak acid with 2 protons. You're going to have it can lose 2 protons, so you're going to have 2 buffering regions. So the first buffering region is when you transition from H2SO3 to HSO3 minus, okay, and then the second buffering region would be HSO3 minus to SO3 2 minus. Okay. Amino acids can actually act as polyprotic acids. You'll see a lot more about amino acids in biochemistry if you go on to biochemistry. But sometimes you'll have a side chain that has a proton that can be ionizable, and then you have a acid group, a carboxylic acid group that's in all amino acids. Okay. Sorry, this is not the side chain, it's the amino group in the amino acid. So all amino acids have this amino group and a carboxylic acid, right? So they lose that first proton off the acid group first, and then they would lose the second proton off of the amino group. Okay, so moving on to solubility, right? We've covered all the acid-base material for the quarter now. We're moving on to solubility. And in the first quarter of general chemistry, we introduced solubility rules to determine when something was soluble. I did not expect you to memorize those solubility rules. I still really don't expect you to memorize these, but I'm introducing them again just as a reminder. The more you see them, the more you might be able to kind of pick them up and remember them. In this class, you can kind of consider, we're talking about the equilibrium, the equilibria of these systems, and for the most part, we're going to be talking about things that are insoluble in this section. So you can kind of just assume, all right, these are insoluble. But what are the guidelines? Well, there's certain things that are always soluble, and those are group 1 ions. The alkali metals are really always we consider those as always soluble, and ammonium, NH4+. Soluble anions that are always soluble, nitrate, NO3-, and acetate, CH3COO-. The halides, group 17, those are typically soluble except when they're combined with gold, copper, lead, and mercury. Right? And then sulfates, SO4 2-, except when they're combined with lead, mercury, calcium, barium, strontium. So lead and mercury again show up, but then all the group 2 metals here for the sulfates. Sulfate doesn't like those. Okay. So anything you combine anions or cations that aren't listed above here are going to result in formation of insoluble compounds. Right, so things that are always insoluble, hydroxides are usually always insoluble, except when they're group 1 metals or group 2, some of the group 2s. Sulfides are always going to be insoluble except group 1 and ammonium, and then calcium, strontium, barium, the group 2s. Carbonates, again, except for group 1 and ammonium, and phosphates except for group 1 and ammonium. Well, the term insoluble, in the first quarter of general chemistry, we kind of considered that to be, making a precipitate and it's solid, right? You convert it into a completely solid, none of it's left in solution. But it turns out that that term insoluble really means that it's only slightly soluble. So there is a small amount of these compounds that are dissociated and in solution. Okay. For a slightly soluble ionic compound in water, there's an equilibrium that exists between the solid state and the aqueous state. And we can write that equilibrium if we do, let's say, lead fluoride solid. If you try to dissolve some of that in water, you're going to get some of it to dissociate into lead 2+ ions and 2 fluoride anions. Okay. Right, so there's this equilibrium. The equilibrium for something that's only slightly soluble, or that we would term as insoluble, the equilibrium lies far to the left. Okay, you can write a reaction quotient for this, okay, and that would be your concentrations of products divided by the concentration of reactant. But remember that that reactant concentration there is a solid, so that usually doesn't really factor in, right? So that's where we get this QSP, and that SP stands for solubility product. Okay, so the solubility product is going to be, if we break this up, it'll be the QC times PbF2 for the solid, which would just be our products that are dissolved into solution. Okay. QSP is the ion product expression or solubility product expression for any ionic compound. So our generic, we can write a generic form of this, QSP. For our compound, that would be MX, and then the P and Q are the coefficients, right? For any of those, we're going to have the concentration of M raised to that power, whatever that coefficient was, times the concentration of X raised to that power. So these are pretty easy, okay? You just look at the formula of the ionic compound you're looking at, and that QSP is going to be, the concentration of each of the ions in it multiplied by each other. Right? When the solution is saturated, the system is at equilibrium. And that's where QSP equals KSP. And that's what we term as the solubility product constant. Okay? Q is, at any point. K is a constant because it's at equilibrium, or for this case, when we say it's at equilibrium, when the solution is saturated. No more of this compound can dissolve in water. And thus the KSP value of a salt indicates how far the dissociation proceeds at equilibrium. So how much of this can dissolve in water? That's what the KSP tells you. So the larger the KSP, the more of that salt can be dissolved in water. So let's try a problem writing these. Okay, so we're writing the ion product expression at equilibrium for each compound. So magnesium carbonate, iron 2 hydroxide, calcium phosphate, and silver sulfide. Okay, so the first thing we need to do is write the chemical reactions that are occurring here. So magnesium carbonate. Right, magnesium's +2, carbonate is -2, so they're in a 1-to-1 ratio. So when it dissolves in water, we get, and I should put, that's a solid, right? Magnesium would be a 2+ ion, aqueous, plus CO3 2- aqueous. And then we're going to write the ion product expression, QSP, at equilibrium, right? So remember, at equilibrium, that equals KSP. That's just kind of semantics, right? The way we calculate them is the same. It's just going to be the product concentrations multiplied by each other. So here we have Mg2 plus multiplied by CO3 2 minus. Okay, pretty simple. Okay, B, iron 2 hydroxide. That 2 means iron has a +2 charge because iron, transition metal, it can have multiple charges. OH minus, it always has a -1 charge, so we need 2 of them to balance that +2 charge on iron. So when it dissolves in water, we'll get iron 2 plus 2 OH minuses. And now our KSP becomes iron 2 plus times OH minus concentration squared. Okay, because we have this 2 there in that balanced equation. C, we have calcium phosphate. Now this gets a little bit tricky. Calcium is a +2 charge. Phosphate, PO4, has a 3 minus charge. So we have a 3 minus and a +2. So to balance this, we need 3 calciums and 2 phosphates. So we're going to get 3 Ca2 pluses when it's dissolved, and we'll get 2 PO4 3 minus phosphate ions aqueous when it's dissolved. So now our KSP would be calcium 2 plus to the 3rd power times PO4 3 minus phosphate to the 2nd power. Okay, and that is about as challenging as that this type of problem could get. Just remembering to keep those charges in there. All right, silver sulfide is the last one. We have silver and sulfur. Sulfur is a -2 charge, just like oxygen would be. So silver is a +1. So you're going to need to have 2 silvers per sulfur. So we get 2 Ag plus aqueous plus S minus aqueous. And our KSP is silver plus squared times S minus. Okay. So here's a table of some of the KSP values, for some of these compounds. Don't have to memorize these, but you can see how great a difference there is in some of these. Something like aluminum hydroxide, very insoluble. KSP is 3 times 10 to the minus 34. Then something like zinc iodate, it has a KSP of 3.9 times 10 to the minus 6. So that's a big spread. And then silver sulfide, even less soluble, right? 8 times 10 to the minus 48. So the range in these KSPs can be quite high. Okay, let's try practice determining KSP from the solubility. So if we have, in this problem, we have lead 2 sulfate is a key component in lead acid car batteries. Its solubility in water is 4.25 times 10 to the minus 3 grams per 100 mils of solution. What is the KSP of lead sulfate? And then the second part of this, when lead 2 fluoride is shaken with pure water at 25 degrees Celsius, the solubility is found to be 0.64 grams per liter. Calculate the KSP of PbF2. Okay, so we have 2 of these to calculate. Okay, so for the first one, we have lead sulfate. Sorry, that's a solid, and we can write this equilibrium as such, and we can write our expression for KSP is concentration of lead 2 plus times the concentration of SO4 2 minus, and we're done with that. Okay, now we can look at what is our solubility, and we're told we get 4.25 times 10 to the minus 3 grams of lead sulfate per 100 milliliters. Well, we need it in a concentration of moles per liter. So how would we do that? Well, we'd need to divide by our molecular weight, which is something like 303 grams per mole. And then we need to convert milliliters to liters. So 1,000 milliliters would be 1 liter. Okay, so when we do all of that, we should get 1.4 times 10 to the minus 4 moles per liter for lead sulfate. So if you have a certain number of moles of lead sulfate, by the balanced chemical equation, you're just going to get the same number when it dissolves, right? You'll get 1 mole of Pb2, and you'll also get 1 mole of SO4 2 minus. So this concentration that it gives for the solubility of that compound is going to equal the concentrations for both lead and sulfate. So now we can use our KSP expression, Pb2 plus times SO4 2 minus, right? We're given that value, right? And so that's going to equal 1.4 times 10 to the minus 4 molar for both Pb2 plus and SO4 2 minus. So we're just squaring that essentially. 1.4 times 10 to the minus 4 squared. So our KSP is 1.96 times 10 to the minus 8. Okay, for the second part, for lead fluoride, PbF2, solid, we're going to get Pb2 plus 2F minus. So now it's a little bit different. We're going to have a coefficient to keep track of. So our KSP now is going to be Pb2 plus times F minus squared. And we're given our concentration as 0.64 grams per 1 liter. So we divide by our molecular weight, 245.2 grams per mole. And we'd get moles per liter. So this would be 2.6 times 10 to the minus 3 molar, or moles per liter. Right, so from our balanced chemical, and this is for the compound, remember, this is for PbF2. So to get the concentration for Pb2 plus, there's 1 mole of Pb2 plus for every 1 mole of the compound. So that's just going to be the same number, 2.6 times 10 to the minus 3 moles per liter for Pb2 plus. The concentration of F minus now, there's 2 moles of F minus for every 1 mole of PbF2. So we'd multiply this by 2. So that would be 5.2 times 10 to the minus 3 moles per liter for F minus. Now we can plug this into our KSP expression, right? It equals concentration of lead 2 plus 2.6 times 10 to the minus 3 times 5.2 times 10 to the minus 3 squared for F minus. And we get something like 7 times 10 to the minus 8. Okay, so that's how we would calculate KSP's given solubility of slightly soluble inorganic compounds. Right. Let's try another one of these. Calcium hydroxide is a major component of mortar, plaster, and cement, and solutions of calcium hydroxide are used in industry as a strong, inexpensive base. Calculate the molar solubility of calcium hydroxide in water if the KSP is 6.5 times 10 to the minus 6. So now we're given a KSP value, and we have to calculate how much would dissolve in water. And this is probably a more applicable question to real-world situations, because typically you can look these KSP values up. So we have to set this one up as an equilibrium. So we have calcium OH2 solid going to Ca2 plus aqueous plus OH minus aqueous, and there are 2 of them. Okay. We're given a KSP value, we're given the KSP value, but we can calculate the KSP expression. That is going to be Ca2 plus OH minus squared. Okay, and we know that equals 6.5 times 10 to the minus 6. Okay. Right, so when we're doing our ice table, our reaction table here, calcium hydroxide is a solid, so we're not really going to be concerned with that, right? Because remember, the concentrations of pure solids don't change. Right? We're going to start with, or assuming we start with 0 for both of these, right? Right when we put that into solution, there's not going to be any of those around to start. And then when this dissolves and starts to solubilize, how much do we produce? Well, usually we have been using X as the variable, but the book likes using, for these types of questions, S's as the variable for solubility. You can still use X if you prefer, but we get plus S for calcium and plus 2S for hydroxide, because this 2, right? There's going to be twice as much OH minus produced when this dissolves as there are calciums. Okay, so at equilibrium, this would be S and this would be 2S. Okay, so now our KSP, we can plug those values in. It would be S times S squared, 2S squared. And that would equal, when we multiply that through, 2S squared would be 4S squared times S would be 4S cubed. Okay, very easy to mess that math up, but just remember your order of operations, right? 2s squared would be 4s squared, but then you're also multiplying by another s, so 4s cubed. Okay. That equals 6.5 times 10 to the minus 6. Right, so now we can solve for s. So s is going to be equal to the cubed root of KSP over 4, which would be cubed root of 6.5 times 10 to the minus 6 divided by 4, which would be 1.2 times 10 to the minus 2 molar. Okay, so then we could, if you wanted to ask, how much calcium is dissolved, that'd be that number. If you wanted to know how much OH minus, the concentration of OH minus was, that'd be 2 times that number. Okay, so the relationship between KSP and solubility is shown here, right? The KSP value shown here, right? If you have 2 ions, right, as you decrease in KSP value, the concentration is going to decrease. Okay, now we have 3 ions in these, so you can directly compare them as well. So this is the descending order of KSP, and you'll see that the concentration is going down. You'll notice if you try to compare, a one with 2 ions to one with 3 ions, that's a harder direct comparison to make. There's a term called the common ion effect, and the book talks about this. So if lead 2 chromate in this solution, we have lead 2 chromate in equilibrium with lead 2 plus chromate. It's slightly soluble, so it forms a precipitate in this solution. When you add sodium chromate to this solution, right, so you've had this saturated lead 2 chromate solution, to that you add sodium chromate that would normally be soluble, right? The chromate concentration in solution now goes up because you've added some of that, right? And what that does via Le Chatelier's principle, right, you've added some of this product, so you're going to shift your equilibrium to the right. Right, so the common ion these both share is chromate. So that common ion effect will shift that equilibrium to the left, and you'd actually precipitate out more of that salt, the lead chromate salt, in this solution. So let's try a problem using this principle. We calculated the solubility of calcium hydroxide in water. What is its solubility in 0.1 molar calcium nitrate? Right, now we have the common ion now is calcium, okay, and you have the KSP value again of calcium hydroxide is given. Okay, so we're going to have to figure out this added calcium in solution, how that shifts our equilibrium. Okay, so let's remind ourselves what our equilibrium is. So our equilibrium is calcium hydroxide, solid, in equilibrium with calcium 2 plus OH minus, aqueous. Okay. And right, the pure solid, we don't really care about those in our reaction table, so initial change equilibrium. Okay. Now we're not starting with 0 calcium 2 plus. We're trying to dissolve this into a solution of calcium nitrate. Yep. So we're going to have some calcium 2 plus ions already in solution from that calcium nitrate. And we're told that we have a 0.1 molar solution of it, right? So this is going to dissolve completely in solution to calcium 2 plus 2 nitrates. So if we add 0.1 molar of the compound, right, there's a 1-to-1 ratio of calcium to the compound, so it's going to be the same concentration of calcium 2 plus, 0.1 molar. So we're starting with 0.1 molar now for calcium, and a 0 again for OH minus. So our change, just like before, when we try to determine how much is soluble, would be an S, and for OH minus it's 2S. So now our equilibrium becomes 0.1 plus S for calcium, and OH minus again is 2S. So our KSP, same expression, calcium 2 plus times OH minus squared. So now we have, if we keep track of that S, it's going to be, pretty, the math will be more challenging. So again, we're going to, as we've been doing before for our other equilibria expression, we're going to make a simplifying assumption. And we're going to assume that this is about equal to 0.1, right? S is going to be much, much smaller than the amount we started with. So we're just going to call that 0.1. So now our KSP becomes 0.1 times 2S squared. Okay, so that's, we can try to solve for S now. So that's 4S squared equals KSP divided by 0.1. And we know what I wrote that backwards, KSP. We know what KSP is. It's 6.5 times 10 to the minus 6. You can divide that by 0.1. Multiply both sides by 4. That would be S squared equals divide both sides by 4. So we have S squared equals 6.5 times 10 to the minus 6 divided by 0.4. Take the square root of both sides. And what do we get? We get S equals 0.00403, which is about, let's write it in scientific notation, 4 times 10 to the minus 3 molar. Okay, so we'll pick up there in solubility for next lecture.